Alright, hello class. Alright, so we're going to look at an adiabatic process. So remember, an adiabatic process, that means there's no heat exchanged with the environment. So no heat going out or coming in. Now, there's kind of two ways this could happen in practice. One, if you have a very well insulated container that separates your system from its environment so no heat can flow through it. That'd be one way. But probably a more common way is something that happens very rapidly. Like say you have like your car, unless you have a Tesla or something, or an electric car. But if you have a cylinder, you put gas in it, and then the spark plug lights the gas and you get like a little explosion. And that's a kind of a somewhat adiabatic process because it happens so quickly there's not much time for heat to flow. Now obviously some heat does flow because your engine will heat up. But yeah, things that happen very quickly, flow of heat takes time. So to a good approximation, something that occurs quickly would be an adiabatic process. And what we're going to do is we're going to look at so I wrote down here we have our first law of thermodynamics. The change in internal energy, that's the specific heat of a gas at constant volume times the number of moles times the change in temperature. Saw that from the last video. And then of course the ideal gas law. But what we want to do is we want to look at infinitesimal changes. So I'm going to rewrite these in infinitesimal form. However, we're also going to set Q equal to 0. So what we have is dE is equal to dW, which is, I guess I should have written one more equation. So remember, if we have like a PV diagram, for any process, the magnitude of the work is equal to the area under the curve. And so, the total area under that curve would be the integral of P dV. P is on the vertical axis. So we'd have like our rectangle here, where the area would be whatever the pressure is here times the width, which is dV. And so, because of our convention that W is positive when we're doing work on the gas. So here, if dV is positive, that means that our gas is expanding and doing work on its environment, and so it should be losing energy. And so we have this minus sign in front. Okay, so now let's write down this infinitesimal version of these laws. All right, so the first law, we can say dE is equal to dW, because Q is 0, so we have minus P dV. And dE internal is CV and dt. So those are the infinitesimal versions of those equations. And we can also look at, we'll do that later. We'll do that when we need to. We can also take the derivative of each side of the ideal gas law. We'll do that later though. Okay, so let's get started. We have the ideal gas law. Yeah, let's do that. Here, let's start here. We have the change in internal energy is equal to we wrote that down over on the right. And this is also equal to minus PdV. Because, in this case, dE is, we just set these equal to each other, basically. Okay. So we've got that, and let's kind of solve for dt. We will need that, let's solve for dt. So that'd be minus P dV divided by the specific heat at constant volume times N. And I'm going to write this off to the side as well. I'm kind of worried about board space on this. What we're doing is going to take a bit of work. So, let's outline what we've done, and then I'm going to write the result over on the board on the right. So basically, we have these infinitesimal versions of the equations above. dE is minus PdV, and dE is also equal to Cn delta T, or dt. So we set these equal to each other and solve for dt. Math people might object to that term, solving for this, like it's a variable. But let's write down the result. Okay. And now let's look at the ideal gas law. I'm going to leave a little space here. So what we want to do is let's differentiate both sides. So here, let's write it like this. We're differentiating both sides of this. So from the chain rule, we have a product here. Both these are variables. So we can say P dV plus V dP now the N and R are constant, so we can take those out. And then we have, just on the right side, we have NR dt. All right, so that's just the ideal gas law. We take a total derivative. And, we've got this dt. We're going to wind up plugging that in as well. Let's see. Let's plug that in. So we have PdV. That's equal to NR. Now dt, we're going to have a minus sign. So that would be P dV divided by CV times N. We'll get a little cancellation here. So this is minus R I believe that is correct. We got rid of the N. So okay, that looks good. Now R, I didn't write this one down, but R is Cp minus Cv. So that's true for any type of gas. So R is always Cp minus Cv. And let's plug that in. So here we have minus, and then we have Cp minus Cv divided by Cv. and I'm a little worried about space on the board. So what we have is minus, we have two fractions here, Cp over Cv. Again, remember that this first term, Cp over Cv, is just gamma. And then, so we have gamma minus Cv over Cv, which is 1. So I'll rewrite this result here. P dV plus V dP equals, and then it's minus gamma minus 1 times P dV. We can write it this way. Just distribute the minus sign and flip it around. 1 minus gamma. Okay. Now we can distribute this. So this is P dV minus gamma P dV. And we get some cancellation here. This P dV term cancels out. So what we have is V dP. I'm going to write it like this, plus gamma P dV equals 0. All right, so this is kind of an important result. Now, we're not done though, but yeah, V dP plus gamma P dV equals 0. And then what we're going to do is let's integrate both sides. Now, let's do this. The integral of V dP plus gamma times the integral of P dV is equal to the integral of 0, which is a constant. And now what I want to do, actually maybe I should have done this before integrating. Yeah, sorry, let's do this before integrating, but then we'll integrate. It's going to be very similar to this, but let's multiply both sides by 1 over PV. Well, yeah, that won't change the 0 here. So if we do this, 1 over PV times VdP, this is dP over P plus gamma. And then the P's cancel out. We have dV over V. And, sorry, that's equal to 0. Okay, so it's in a slightly better form. Now let's integrate both sides. So we have the integral of dP over P plus the integral, plus gamma times the integral of dV over V, and now that's equal to a constant. All right, now this is just the natural log of P. And the integral of dV over V is the natural logarithm of V. So we're kind of getting to our final result. It's a very important result, which we're going to use later. But we can, remember, from these properties of logarithms, I'll do this in 2 steps. I'll just say C for constant. So remember, like if you have the natural log of V to the, say, gamma power, that's equal to gamma times the natural logarithm of V. And now when you're multiplying these, you multiply the logarithm of x plus the logarithm of y is the logarithm of xy. So our kind of almost final result. We can combine these. Where the natural logarithm of p times v to the gamma is equal to a constant. Now that means p times v to the gamma is a constant, or it's e to whatever that constant was, but e raised to some power, like e raised to a constant power, is also a constant. So the result here, I'm just going to write it up here. PV to the gamma is constant. So this is true for an adiabatic process. Now, if you have like an ideal, like a monatomic gas, gamma is 1.67 roughly, which is greater than 1. Now, let's look at what this would look like on a PV diagram. Because typically, gamma is actually always going to be greater than 1. Gamma is Cp over Cv, and Cp is always going to be bigger than Cv. So, yeah, so if we have a PV diagram, now let's go back to the ideal gas law for a moment. Now say we have an isotherm. Isotherm means constant temperature, and of course N and R are constants. So for an isotherm, we have P times V as a constant. And we know what those look like. They're hyperbolas, like mathematically it's like y equals 1 over x, or x times y is equal to 1, which is a constant. So same here. If we multiply our two variables, it's constant. So if one is big, the other is small. So if the volume is small, pressure is big, volume is small. So this would be like one isotherm here. This would be another isotherm at a different temperature. So this would be like temperature T1, that's temperature T2. Now an adiabatic process would look kind of similar, but let's say we have a monatomic gas. If we look at, if we solve for P. For an isotherm, P would just be C over V. Well, here V is raised to a power that's greater than 1. So an adiabatic process would kind of look the same, but it's steeper because gamma is greater than 1. And so these are isotherms. This is an adiabatic process. So it kind of looks similar, except it is steeper. And this result in particular is going to be pretty important later on. There's another way we can write this using the ideal gas law. Let me see if we can work this out. So I start with the ideal gas law, and we can write it like this. Or actually, no, let's start with PV to the gamma is equal to a constant. We can write it like this as well. PV times V to the 1 minus gamma is a constant. And, just when you have, that should be gamma minus 1. Well, it's like you can, if there's no exponent written there, it's obviously 1. So if you have the same base, you add the exponent. So 1 plus gamma minus 1, that would just be v to the gamma, which is what we have here. And so then PV is nRT. Wasting a lot of ink just writing constant every time. I should probably just call it C. But now if we divide by nr, we have a constant divided by another constant, which is a constant. So we can write it like this. So just another way of writing this for an adiabatic process. The temperature, the absolute temperature, times the volume to the gamma minus 1 power is equal to a constant. All right. So yeah, this result is definitely going to come up again. It's very important. So I'm going to do a kind of a quick video showing that. And I think that'll be all for this video then. So yeah, we'll leave it here. And just remember that result for later.